Here I have assumed that M2 was at rest in the beginning. That doesn't have to be the case, but the method is in front of you. Just apply conservation of linear momentum along different directions. If it is 3D, then Z direction will also come. And if it is not elastic, then conservation of kinetic energy, COKE, won't come. A typical two-dimensional case can be that of a bomb exploding and its fragments going in different directions. So initial momentum is 0, and finally different components having different velocities, alpha, beta, gamma, 3 angles, if there are 3 pieces. You will just apply conservation of linear momentum along x direction and along y direction. So that's how we handle 2-dimension case and even 3-dimension case. Now, every time collision does not have to be head-on. In fact, in this type of situation, like a cut in carom board, it can't be head-on. If one coin hits the other coin absolutely straight, means center to center, then they will travel in the same line after the collision also. It will be motion, it will be collision in 1D, and also motion in 1D. If it's a cut, then the 2 coins can go at some angle different from 0 or 180 degrees. So that cut, how does it work? Imagine a ball or a coin, carom coin, here another coin here, or a ball here. Now let me make it somewhat smaller. Now imagine this fellow not going in center to center line, but going at some line like this. So it's heading towards, let's say here, its center is heading towards there. So when the center reaches somewhere here, you find the collision taking place. If the center is somewhere here, draw a circle and you find a collision taking place. Let me try to show it. Now, when 2 bodies interact, there will be normal reaction force. It will be normal. That is the line of action, if you like. And along that line, you have to consider velocity of separation, velocity of approach, when you are talking about the coefficient of restitution in such cases, that you must note down. Consider E along that line. So appropriate components will have to be taken. Now, linear momentum is anyway conserved. It's about how you choose x and y direction. In the case like this, we prefer to choose one direction as the tangential direction and the other direction as the normal direction. Normal direction you must have understood already. Why? That's how we talk about E, or line of action. So one direction will be the normal direction, other direction will be the tangential direction in such problems. That's our choice, of course. There are no rules. These are choices. Tangential and normal direction. Now, why so? One reason for n, I told you, normal direction. There's one more reason. When the two bodies interact, the forces are along normal direction. That means along the tangential direction, there is no force. There is no force. Along the tangential direction, there is no force. So if I treat one body as a system also, not both of them jointly as a system, if I treat one body as a system, then I can say that for that body there is no force along this direction. So if that body had some velocity v1, then the component of v1 along the tangential direction would never change. The component of v1 along the tangential direction would never change, never. For one body as a system. Likewise, I can take the second body of the system also and say the same thing for the second body. Velocity along tangential direction cannot change, component of velocity. And that is quite useful. So you must make note of this point, that in oblique collisions it's very convenient often or mostly to choose tangential and normal directions as x and y directions. And then you apply COLM, etc. And you apply this also, that velocity along tangential direction would be constant, and proceed further. You can see that there is a spherical body whose radius is r. This is a small particle. Traveling with velocity, this spherical body is at rest It collides elastically. What are the final velocities? Velocity. So the collision would take place somewhere here. Force is going to be normal. So as I mentioned earlier, we will take two directions, one normal, other tangential. Call them x-axis or y-axis, or call them tangential and normal directions. The force will be in this direction. So in this direction, velocity cannot change. Here comes the particle. Velocity has this direction, and the component of velocity along this direction will not change. And that won't change for the ball also. Well, so can you tell me in which direction will the ball go? In which direction will the ball go? In the direction of n is the correct answer, but can you be more specific? This or that, right or left? Along this line, right or left? I'm talking about this ball. In which direction will it go? This ball, along right or along left? Answer is along right. And that's because n will act in this direction for the ball. For the particle, n will act in this direction. This is the line of action. For the ball, n is this direction. For the particle, n is this direction. The ball will go like this. But for particle, we cannot say that it will go like this. In fact, it won't be correct. The particle won't go like this, because particle has some initial speeds. Ball did not have an initial speed. So in whichever direction force was applied, ball moved in that direction. Alright. So let's say ball going in this direction has velocity v double dash. Particle, this will be somewhat challenging. Particle, let's say, goes in some direction having velocity v double dash, or rather v single dash, and making an angle of theta, let's say, with this. So along tangential direction, velocity cannot change. That means v dash cos theta must be what? Can you tell me which what should come here? V dash cos theta. Component of V along this should be what? What should come here? I repeat, which component of V is along this direction? That's not a clear answer, sine or cos. Which angle are you talking about? Cos of what? A sine of what? Same theta. Okay, let's see. If this is theta, then that would be 90 minus theta. How are you getting theta? This is 90 minus theta. After that, how do we know this angle is theta or something in terms of theta? V dash is not making 90 degrees with V. We are not saying that. So this is 90 minus theta, but this we can't write in terms of theta. Let me use another angle, maybe phi. So now you can answer. In terms of phi you can answer, I hope. V cos phi, V sin phi. Sine, let's see, phi 90 minus phi, 90 minus phi. Yes, sine phi. Okay. And by the way, phi is not a problem actually. This is rho, and this is the radius. So we already know what phi is. Tan phi is rho divided by, in fact, sin phi is rho divided by r. So we know this. Okay, now two unknowns, three unknowns. V dash, theta, V double dash. Three unknowns. One equation at the moment. Next equation would be, okay, question says elastically. Fine. So one equation will come from energy, kinetic energy. One equation should come from COME along N. Why N? Because along tangential direction I already have this. So let's see. Masses of these two are equal. Masses are not given, but they are equal. So M V, which component along N? Cos then the big fellow is at rest. Finally, big fellow is going along n only, and the small fellow is going here. So mv dash sine theta, but v dash sine theta is in this direction. Well, this is COLM. Now COKE. Alright. 3 equations, 3 unknowns. Can you find them? V dash theta and V double dash. What I will do is that I will put up the answers. And then you can see if you are getting them. V double dash. V double dash should be V by R under root R square minus rho square. Then V dash, V times rho by R, then theta. It appears that theta is 0. And now you can raise your hand if you would like this to be discussed on the board further. Alright, I will wait for some more time and then I will move on. Or you can raise your hand. Let me clone the screen. The third equation, the Koch equation, we divide by m by 2. we get rid of phi. So we have sine phi equal to or maybe later. So let me keep sine phi right now, cos phi also. There are three variables. We first get rid of theta, let us say. Let us try that. Okay, I can cancel m also. M. Now we get rid of theta. Squaring and adding. Let me first rewrite this. Now squaring and adding. These fellows, just v square theta is gone. Now let's get rid of the next variable, v dash. V dash square is given by v square minus v double dash square. Now cancel v square. V double dash cannot be 0. Big body will be hit. It can't have 0 speed. So since v double dash can't be 0, we can cancel it. 0 can't be cancelled. So v double dash is v cos phi. And how much is cos phi? Base r square minus rho square under root upon r. So that's about v double dash. Now you should be able to find other variables. What makes rocket move? when gases come out of the rocket, just like bullet comes out of gun and gun experiences force in opposite direction, the same way gases come out and the rocket gets a thrust. So it's like bullet gun system, but with a difference that mass is coming out continuously. In case of gun bullet system, bullets don't come out continuously. They come out in packets, if you like, packets of masses. Maybe a machine gun loaded with bullets and firing is done continuously, that comes somewhat closer to rocket system. The fuel is burned in good amounts in rockets, so mass is going to fall. So it is not a system of constant mass. It's a system of variable mass. Till now our discussion was primarily on fixed masses. Even Newton's second law, if you see, force equal to mass times acceleration, is not going to be valid here. Force equal to mass times acceleration is not going to be valid here, because force is the rate of change of momentum, and it becomes ma if you can take mass out from differentiation, and then dv by dt is acceleration, and you have force equal to mass times acceleration. So Newton's second law, mass times acceleration, is okay for most purposes, but generally speaking Newton's second law should be rate of change of momentum, because then you can handle cases like these where mass can also change. Let's say the gas is coming out at constant rate R, let's say at t equal to 0, the mass of the rocket is m0. When I say mass of the rocket at t equal to 0, the fuel is inside it, so it takes into account the mass of the fuel also. At time t, gases are coming out at constant rate, so mass falls. At time t, mass becomes capital M. So obviously, and let me also say that R is a positive number. So obviously, M will be M0 minus RT. We are assuming R to be constant. Let's say at time t, the speed is v, and just like we assumed R to be constant, let's also assume that with respect to the rocket, fuel goes out at a constant rate. With respect to the rocket, exhaust I should say, or gas. With respect to rocket, gas ejects with U. With respect to rocket, you will always see gas going downwards. So U is downwards, right? So at time t, mv. Now consider t plus delta t. Consider delta t after t. Consider delta t time after t time. What we are going to do? We are going to apply for the rocket gas system conservation of linear momentum. Rocket gas system in time delta t. That's what we are going to do. That means between t and t plus delta t, which is same as saying in time delta t. So at t, obviously mv is the linear momentum. At delta t, that's what we are going to discuss. So let's say in delta t time some gas comes out, and when gas comes out, it will impart some momentum to the rocket. So some mass is lost and some speed is gained. Let me say delta m is the mass lost. In fact, delta means final minus initial, and final mass is less than the initial mass. So delta m would be negative. If I want to make delta m positive, then I can call it as the mass of the gas. Or let's do it like this. Let's say change in the mass is delta m, change in the mass, in time delta t. Now when we say change in mass, then it means that the change means final minus initial. Then delta m is negative. Change in mass has to be negative, because final mass of the rocket is going to be lesser than the initial mass of the rocket. And if delta m is change in mass, it must be negative. So in delta t time, delta m change mass takes place. So minus delta m would be the mass of the gas which comes out. Minus delta m is positive. Now V becomes, let's say, V plus delta V. Let's write here at delta t. M becomes m plus delta m. Delta m is negative. V becomes V plus delta V. Okay. We are going to apply conservation of linear momentum, and we will do it with respect to some stationary object, observer, some stationary observer at some frame, reference frame somewhere else. For that observer, now when I say this V, the velocity of the rocket, it is all with respect to that stationary observer. But when we say U as the velocity of the gas with respect to the rocket, it is with respect to the rocket. If you want to apply conservation of linear momentum, you should have only one observer. Can't mix up things. So U also, the velocity of the exhaust also is required with respect to the observers under consideration. So what do you think would be the velocity of the exhaust with respect to some stationary observer. It can't be u for sure. Velocity of exhaust with respect to this observer let me just say O. Velocity of gas with respect to rocket, velocity of rocket with respect to O, where O is stationary observer. The velocity of gas with respect to observer in upward direction. We know that gas looks going downwards for the rocket, but with respect to the stationary observer, we are considering it upward direction. Upward direction we are considering. Velocity of gas with respect to the rocket is downwards, u. But in upwards, minus u. Velocity of rocket with respect to observer, that is v. So that's VGO upward direction. Now we apply COLM in upward direction. So at time t and at time t plus delta t. At time t it was just mv. And at time t plus delta t, m became m plus delta m, where delta m is negative, of course. So m has decreased, v has become v plus delta v. Delta v must be positive. If gas comes down, the speed should increase. Then we are talking of rocket and gas system. So the gas delta m mass which has come out, what happens to that? Delta m mass that has come out. Well, actually minus delta m mass has come out, a positive number has come out. Minus delta m is the mass of the gas. And what is the velocity? Minus u plus v in upward direction. Right? That should be fine. Yes. So let's open right side. Cancel as much as we can. That's it. We want delta V by delta T. Delta V, let's group. Delta T will come. We can group delta M right now. Okay. So m plus delta m well, these two also. No. These two. V delta m, V delta m. V delta m, V delta m. Now we want delta V by delta T. We said R was constant. Rate at which gas was coming out, that was constant. That means, and we said it was positive also. So R is minus delta m by delta T. Now, taking limit delta T tending to 0, in fact it can be done orally after this, that will become dV by dt which is gone, UR by M. Now dr by dt is the acceleration, that's why we wanted it. So acceleration is given by UR by M. It's not constant. Why? Because we said U was constant. No, we said R was constant. We said U was the velocity of gas with respect to the rocket. Capital M was the instantaneous mass. So U was constant, so to say, with respect to the rocket. But rocket speed itself is variable. So with respect to our observer, U is not constant. With respect to our observer, R is constant. U is changing. Capital M is changing. In fact, capital M is decreasing. Capital M is decreasing. Mass is falling and falling. U as a number is with respect to the rocket. So when you put some numerical value for U, then that numerical value will be the same. Velocity of gas with respect to the rocket, numerical value is fixed with respect to the rocket. So that way we will fix some numerical value for U. We will fix some numerical value for R. We can't fix numerical value for capital M because it will change with time. So if capital M falls, then A must rise. Acceleration is variable and it is increasing. Acceleration is increasing. Any questions up to this point? If you have, let me know. We are still doing theory. No assignment for today. We stop now.